Let's go through the example in the goodness of fit test. Example 1, it is believed that the blood type ratio for blood group O, A, B and AB is 50, 23, 23, 4. So here we have a sample of 200 students chosen at random, shows the following data. So given from the sample chosen, we have 105 of students that have blood type O, 50 students have blood type A, 33 students have blood type B, and 12 students have blood type AB. So now, do we have reason to accept the above ratio at 0.01 level of significance? So from the problem, these frequencies, this value is denoted as our observed frequencies, given as OI. So now what we need to do is, first of all, we have to state the hypothesis. So we want to check whether do we have reason to accept that the ratio of the blood group O, A, B and AB is 50, 23, 23 and 4. So that is our null hypothesis. That given as the ratio of O, A, B and AB is 50, 23, 23 and 4. And the alternative hypothesis would be the counter of the null hypothesis, where the ratio of this is not this one. Now we have stated our hypothesis. Then we want to find the expected frequencies. Which is EI. So if H0 is correct, so we would expect that the number of students with the relevant blood group, for the first one is group O, would be, so remember the formula for the expected frequencies is equals to n times the probability for that category. So the total of the sample, the observation here is taken from this total, 105 plus 50 plus 30 plus 12. So here is the total would be 200 samples, 200 students. So 200 times with the probability for that category. So the probability that the students have blood type O is given from this ratio. So it would be 50 over, so the total of this would be 50 plus 23 plus 23 plus 4. So it would be 50 over 100. So the expected frequencies, the expected number of students for blood group O would be equals to 100. And then for blood group A, 200 times with, so for the ratio for A is 23 over 100, which is equals to 46. And then for B would be 200 times with, so the ratio, the expected ratio, suppose that the ratio is 23 over 100. So it will be equals to 46. And the last one is for AB. So we expect that the ratio for AB is 4 over 100 among the total number of students. So here would be 8. So we expect that the number of students would be 100, 46, 46, and 8. for the relevant blood group. Okay, now next, we combine all this into a table. So I just rewrite all this in a horizontal table. Given the observed value is given as 105. This is for group O. And then for group A is given as 50. Group B is 33. And for group AB is equals to 12. Okay, and the expected frequencies is given as 100, 46, 46, and the last one is 8. Okay, now we want to find the chi-square test. Given the formula is OI minus EI square over EI. So given first I find OI minus EI. So here is the value is 5, 4, 33 minus 46 is negative 13, and this one is 4. Then next I find this value. Just this one. So this one would be 5 square over 100, which is 0.25, and then 16 over 46, 0.35, and then negative 13 square over 46, and the last one is 4 square divided by 8, which is equals to 2. So we find the summation of this, where this is the value of the chi-square, which is equals to 6.27. Next is we find the critical value. Given the chi-square, alpha is given as 0.01 because 1%. So 1% means 1 divided by 100. So please choose the right value for the chi-square, 0.01. And the number of category that we have is, we have 1, 2, 3, 4 categories. So 4 minus 1. So here would be chi-square 0.013, which is equals to 11.3449. And here we have the value of chi-square, which is equals to 6.27. Here is less than the critical value, which means that we have to accept each note. So we can make the conclusion that there exists evidence to support that the blood type ratio for blood O, A, B, and AB is 50, 23, 23, and 4. Okay. So that's how we solve the question. Another type of example is that we have the problem that follows different kind of distribution. So in this example, we have the Poisson distribution. Okay, the number of letters received by an office in a day for 100 days is shown below. So here we have number of letters 0 up until 1, 2, 3, 4 and greater than 5. And these are the number of days for the number of letters. Okay. We want to test the hypothesis that the number of letters received by this office per day follows the Poisson distribution at 0.01 level of significance. So in this case, we want to test whether that the number of letters follows the Poisson distribution. So we know that the Poisson distribution has the parameter mean, okay, mean given as lambda. But if you refer to this situation, this problem, there are no value of lambda given from this. So what we can do is, since we want to check whether this number of letters follows the Poisson distribution or not, we have to determine what are the value of the mean. Okay, first of all, we need to know the value of mean. So given the value of mean is obtained from the, so this is the frequency distribution. What we can do is we can multiply this number of letters with the number of days and total this up, divide by the number of observation. So here we have for number of letters 0 and its frequency is given as 9. Okay, plus with 1 times with 11 plus with 2 times with 24 plus 3 times 25 plus 4 times 19, and the last number of letters given as 5. Okay, 5 times with 12. Okay, so now divide by the total number of observation. 9 plus 11 plus 24 plus 25 plus 19 plus 12. So here we have total of 100. So we get the value of this, which is equals to 2.7. Okay, so this is the value of lambda, which is equals to 2.7. So now we can proceed. Okay, proceed with the hypothesis and then finding the chi-square test. Okay, so now, so we made the hypothesis given that this problem, okay, where we define our x, which is the number of letters received by this office per day. Okay, so our assumption is that this x follows Poisson, given the Poisson is lambda. So our lambda is given as 2.7. Okay, and then the alternative hypothesis would be the number of letters received does not follow Poisson. Does not follow Poisson. Poisson 2.7. Right? Okay, then here, okay, before we find the chi-square test, okay, let us define what is the critical value. Okay, given the critical value is chi-square and we have the significance level used is 0.01. Okay, and the degree of freedom would be different because this is the case is involve the Poisson distribution. So it will be k minus p minus 1. So given k is the number of categories, okay, and p is given as parameter involved in this distribution. So number of categories, here we have k is the number of letters here. Okay, here we have the first category 2, 3, 4, 5, 6. So we have 6 category. And the parameter involved in this problem, here we have the mean, okay, that we found just now, which is 2.7. So which means that we have one parameter. Okay, parameter given as P is equals to 1. Okay, so we consider this mean as one parameter. So the critical value would be chi-square 0.01. 6 minus P, P is minus 1. So 6 minus 1 minus 1 would be 4. Okay, so here will be our critical value, which is 13.2767. So this is our chi-square value, okay, the critical value. Okay, next is we want to find the chi-square test. Okay, so we need to know what is the expected value. So the expected value is given as the total observation times with the probability for each category. So we have PI, or P number of letters. So before we find this expected frequency, we need to determine what is the probability for each category. So the probability for first category, so here let's write down the probability given x is equals to x. Okay, small x is given as 0, 1, 2, 3 up until greater than 5. So here I just write down first the probability of x equals to 0. So x equals to 0. So since this use the Poisson distribution, so we can just use the formula for the Poisson. So given e to the power of negative lambda, so probability of x equals to x is equals to e to the power of negative lambda, lambda to the power of x over x factorial. So we just have to find the value of lambda. Given lambda is 2.7, and this value of x is given as in this bracket. So 2.7 to the power of 0 over 0 factorial, where you will get the value which is 0.0672. Okay, then applies to when x equals to 1. Okay, here would be e to the power of negative 2.7. 2.7 to the power of 1 over 1 factorial, which is 0.1815. Okay, same goes up until x equals to 4. Okay, so there are two ways to solve to find the probability of this. The first one is you use this formula, and the second one is you can find the value from the table. But remember that the table that we use is a cumulative table. So which means that if you want to find the probability of x equals to 1, which means that you have to get the value of x equals greater than equals to 1, okay, from the table, minus with the value of x when x equals to 0. So then you can get the value of x equals to 1. Okay, so now let's just list down here 72, x equals to 1 is equals to. Okay, and you can try out finding for x equals to 2. Here you should get 0.245. X equals to 3 would be 2205. And last one, x equals to 4, which is 0.1488. Okay, so here for the x greater than equals to 5, it will be different, okay, from the rest of the category. So x greater than equals to 5 would be, so how can we find this? It's just that we just find the 1 minus of the total value of x equals to 0, x equals to 1, x equals to 2, up until x equals to 4. So you will get 1 minus 0.863, which is equals to 0.137. Okay, so when you sum up all this probability, you should get, okay, at the end the value should equals to 1. Okay, remember the probability for the discrete, okay, where the total should be equals to 1. Okay, so now we have found the value of the probability. So I just okay. So next is we can find the value of the expected frequencies, given the expected frequencies is n times with p x equals to x. So it will be for the first category, so the total is 100 times with 0.0672, which is 6.72. For the second category, 18.15, $24.5, 22.05, 14.88, and the last one, 100 times with 0.137, 13.7. So you must make sure that the expected frequencies, the total value of the expected frequency should be the same as the total of the observed frequency, which is 100. Okay, so now we can find the chi-square test by taking the value of OI minus EI square divided by EI. So OI is given as 9 minus 6.72 square divided by 6.72, and you should get 0.7734. Okay, for the second category is 2.8167, 0.0102, 0.3947, 1.1407, and the last one is 0.2109. So the total of this would be equals to 5.3466, where this is the value of chi-square test. Okay, so here we have the value, which is 5.3466, given that the value is less than the critical value. So number 4, the chi-square, which is equals to 5.3466, is less than the critical value, which is equals to 13.2767. So since it is less than, which means that we have to accept each note. Okay, so there is sufficient evidence the number of letters received by the office follows Poisson distribution with mean 2.7 letters per day. Alright, so that's how we solve the problem, okay, for Poisson distribution. Now we try the last example, given that this problem follows the normal distribution. So the marks obtained by 200 students are shown below. So here are the list of marks, the category from 55 to 60. We have 6 of students, 60 to 65, 30 students, 65 to 70, 60, and so on. So the total number of students that we have here is 200. Now we want to test the hypothesis that the marks obtained by this student are normally distributed with mean 70 and standard deviation 5 at 0.01 level of significance. First of all, we will state the hypothesis, where we want to test the hypothesis that the marks obtained by this student are normally distributed. So we just assume our X defined as the marks obtained by the students, where this random variable of X follows normal given the mean is 70 and the standard deviation is 5. Okay, and the alternative hypothesis would be the marks obtained by the students does not follow normal distribution. This 5 square because this is variance. Okay, so we have identified the hypothesis. Okay, next is we can consider or we find the critical value. So the critical value is given as chi-square alpha k minus p minus 1. Okay, k is given as number of categories, where here for this problem we have 1, 2, 3, 4, 5, 6, 6 categories. Okay, and the number of parameters estimated from the sample. Okay, so 70 and 5, okay, that is obtained here is not obtained from the sample. We don't calculate these values from the sample. Okay, so which means that the number of parameters estimated from the sample would be equals to 0. Okay, we don't have calculated or we don't estimate any parameters from the sample so that we can generate the hypothesis distribution, because this is simply taken from the question. So our chi-square alpha is given as 0.01. So k is 6, p is 0, minus with 1. So chi-square 0.015 would be equals to 11.0705. Okay, now we get this value of critical value. The next step is we want to find the chi-square value. So here we need to know the expected frequencies. Okay, where the expected frequencies is given as the total observation multiplied with the probability distribution for each category. So here we have our probability is not given, but we know that the distribution of this is the normal distribution. So from each category, to find the probability, we can find using the normal distribution, because our problem is we want to identify that the marks follows normal distribution or not. Okay, so here would be the probability of 55 minus with mean. So mean is taken from the value that is here. Okay, and also the standard deviation. Minus 70 divided by 5. So here would be Z and less than 60 minus 70 divided by 5. Okay, so here would be probability of negative 3. So the z-score is negative 3 till negative 2, and you will get the answer, which is 0.0215. So this can be obtained from the table, the standard normal table. Okay, so here I list all the values of the probability of the marks. Okay, so for the first category, it is equals to 0.0215. Okay, next for the second category, it would be the same. Okay, from 60 to 65. So it will be probability of 60 minus 70 over 5. 65 minus 70 over 5. And you will get the answer, which is 0.1359. Okay, so I'm not going to show you all the steps for this probability because it's just it applies the same method for the whole category. So you can try out by yourself, okay, and check your answer with mine. 0.3413. This one is also 0.3413. And the last one is 0.0215. Right, so we have obtained all this. The next step is now we can find the expected frequencies given the formula is n times with the probability. So the first category, the expected frequencies would be equals to so E1 is equals to, so the total of observation is 200 times with 0.0215, which is equals to 4.3. Okay, for E2 it will be 200 and for the third category fourth category fifth category and the last one is so when you all add all up, you should get the total is 200. Okay, now we have found the value of the expected frequencies. Next is we can find the chi-square test by taking the formula of OI minus the expected frequencies square divided by the expected frequencies. Okay, so here we have 6. Okay, our OI is 6 minus with 4.3 square divided by 4.3, and you should get 0.6721. This one, the same method, 0.2926, 0.9995, 0.1557, 1.7113, and the last one is 0.114. So the total of this would be equals to 3.9452, where this value is the value of chi-square. So now we have get the value of chi-square. The next step is we can make conclusion. So given our chi-square, which is 3.9452, is less than the critical value, which is chi-square 0.015, which is equals to 11.0705, So we can make conclusion that we have to accept H note. Okay, we can make decision that we have to accept H note. So we can make conclusion that there is enough evidence or sufficient evidence that the marks obtained by the students follow the normal distribution with mean 70 and the standard deviation equals to 5.